Okay, so we're going to play a little game called Name That Shape. If I were to sketch this equation, what shape would I get? Right now I see x to the first power, y to the first power, and I know that when I sketch that, I'm going to get a line. Let's go again. What would I get when I sketch this? For this equation, we've got x squared as our highest power. When we sketch this, we're going to get a parabola. Specifically, this parabola is going to be concave up or concave down. It's going to be vertically oriented. If that had been a y squared, we would still have a parabola, but it would be oriented side to side. So if we have x squared or y squared as our highest power, we know we're dealing with a parabola. But what if we have both? If we have, say, I have 2x squared plus 2y squared. I have x squared and y squared. They have the same coefficients. They're both positive. I know in this case I'm going to have a circle. If both of these coefficients had been negative, I would just have to divide the whole problem by a negative, and that would make them both positive, and I would still have a circle. What if the coefficients didn't match, but they were still both positive, like this? I still have x squared plus y squared. They're both positive, but they don't match. In this case, I have an ellipse. And again, if they were both negative, I would simply have to divide the entire problem by a negative, and then they would both be positive, and I would still have an ellipse. But what if only one of them was positive? Like this or like this. For both of these situations, we're dealing with a different shape than we had before. And it doesn't matter if these numbers are the same or if they are different. It's still a different shape, and that shape is called a hyperbola. A hyperbola has the look of two back-to-back parabolas separated by asymptotes that are on a slant, so we call them slant asymptotes. A hyperbola looks like this. The red parabola-looking parts are called branches of the hyperbola, and the blue dashed asymptotes are the slant asymptotes. Hyperbolas aren't always horizontally oriented like this one either. Sometimes they're vertically oriented, so instead of having these side-to-side branches, we would have vertical ones going up and down. But you're not going to have hyperbolas where the branches are next to each other, for example, one up and one sideways. Going back through again, a line you'll see has an x to the first power and or a y to the first power. But no power is higher than that. A parabola will have an x squared as its highest power or a y squared as its highest power. Circles, ellipses, and hyperbolas will all have x squareds and y squareds, but circles will have the coefficients match exactly. Ellipses will have the coefficients not match. Circles and ellipses, though, both of those coefficients will have the same sign. For hyperbolas, it doesn't matter if the coefficients on the squared terms match exactly. They can be the same number or they can be different numbers. What matters is that one of them is positive and one of them is negative. Again, one of the squared terms will always be positive and one of the squared terms will always be negative. So let's go ahead and dive into one of these hyperbolas. Alright, so we have an equation, and immediately I see that I have an x squared and a y squared, but one is positive and one is negative. So that means that I have a hyperbola. I'm going to treat it just like I treated the other equations. I'm going to get my x's with my x's, my y's with my y's, and my numbers on the other side. And then I'm going to group them, but I'm going to make a crucial error in 3, 2, 1 time. I've made an error. Do you see what that error is? By putting the parentheses between the negative and the 25, technically speaking, I factored out a negative, but I didn't actually factor out a negative. I just threw parentheses in there. So to avoid that mistake, we keep the negative with the number, and then we just bring in our own plus sign to separate the terms. So now, just like before, we're going to factor out the coefficient on the squared term, and we're going to factor out the negative with the 25. This is one of those problems where students make very silly mistakes factoring out numbers. It's worth your time to pause for just a moment and distribute to make sure you don't make a mistake when you're factoring out the coefficients. So now I'm going to go ahead and complete my square. So I have 1/2 the middle term, square it, and I'm going to add that to both sides. Leave some room for the y's. And again, just like we saw with circles and ellipses, I'm not just adding 2 squared, but I'm adding 9 times 2 squared. And I'm going to do the same for the y's. 1/2 the middle term, square it, and add that to both sides. But I'm not just adding 4 squared, I'm adding -25 times 4 squared. Notice that negative does in fact get added to the right side when you're adding the numbers. So now I form my perfect squares. First term, last term, middle sign, squared. First term, last term, middle sign, squared, equals, and when I add all these numbers together, I get 225. So I'm going to divide by 225, divide by 225, divide by 225. And just like always, what I do to the top, I have to do to the bottom. So I'm going to divide the top by 9, divide the bottom by 9. That's going to give me x minus 2 squared over 25. And then I'm going to divide the top by 25, divide the bottom by 25. That gives me y minus 4 squared over 9 equals 1. This is what we would call a standard form, but we go all the way to professional form. So I'm going to drop those parentheses all the way down. And that gives me x minus 2 over 5 squared minus y minus 4 over 3 squared equals 1. So without ever sketching a hyperbola before, you can look at this equation and tell me what is the center. The center is opposite, whatever's with x is the x, whatever's with y is the y. My center is 2, 4. What's the horizontal displacement? The horizontal displacement is the bottom of the x term. So my horizontal displacement is 5, and my vertical displacement then is the bottom of the y term. My vertical displacement is 3. Now there are different versions of sketching a hyperbola. I'm going to show you both, but I'm also going to show you the one that I prefer. Some versions stop right here and don't bring in any more information, and it works out okay. But the version I prefer asks another question. It asks, what is the slope of the slant asymptote? The slope of the slant asymptote is going to be like the slope of any line. Slope is always rise over run. And if I was going to say that between vertical and horizontal, one of these is rise, one of these is run, it would be a good safe bet to say that vertical is rise and horizontal is run. And that would be accurate. The slope of the slant asymptotes are rise over run, the vertical displacement over the horizontal displacement. And there are 2 of them, so it's going to be plus or minus 3/5. Let's go ahead and sketch what we have so far. First, I'm going to sketch the center. I'm going to go over 2, up 4, and I'm going to put my point right there. I'm going to label it as 2, 4. Now from here, I know that my slope is plus or minus 3/5. So from this center point, I'm going to go up 3, 1, 2, 3, and then over 5, 1, 2, 3, 4, 5. Put a point there. I could have gone down 3, 1, 2, 3, and then back 5, 1, 2, 3, 4, 5. I only need 2 of those points, and when I sketch in that line, that is my first slant asymptote. Now I go the other way. I'm going to go up 3, 1, 2, 3, and then back 5, 1, 2, 3, 4, 5, or I could go down 3, 1, 2, 3, and over 5, 1, 2, 3, 4, 5. And again, by connecting 2 of those dots, I get my second slant asymptote. So now from here, I just need to get the branches of my hyperbola onto my graph. But I need to know if this hyperbola is going to open in the vertical orientation, up and down, kind of like that, or if it's going to open in the horizontal orientation, side to side, kind of like that. The answer to the vertical or horizontal question comes from professional form right here. When you look at a hyperbola in professional form, one of the terms will always be positive. And by terms, I mean the entire squared term. One of the terms will always be positive, and one of the terms will always be negative. The hyperbola will always open in the direction of the positive term. Stick with me here. Have you guys ever played the game Hungry Hungry Hippos? Do you remember this?
Playing Hungry Hungry Hippos! Hungry Hungry Hippos! Hungry Hungry Hippos is the name of the game!
Okay, so let's pretend for a minute that you are in fact a hungry, hungry hippo, and you're in a zoo, and there are two zookeepers there. And one of them has a big basket of food, tons of food, lots and lots of food, positive amounts of food. Now the other one has a basket of no food, there's nothing in there. In fact, there's so little food, there's like negative food. Which basket of food is our hungry, hungry hippo actually gonna eat? Assuming he doesn't eat the zookeeper. He's going to eat the basket with positive amounts of food, lots and lots of food. And it's the same with a hungry, hungry hyperbola. A hungry, hungry hyperbola will always eat in the direction of the positive term. If the x term is positive, it's going to eat in the x direction. If the y term is positive, then it would eat in the y direction. So because of the positive x term, this hyperbola will open in the x direction. So it's going to be horizontally oriented, kind of like that. But just throwing the branches in there isn't good enough. We need to know exactly where the backs of the hyperbola are supposed to be. Well, if this hyperbola opens in the x direction, which of these, horizontal displacement or vertical displacement, do you think corresponds to an x direction? It's going to be the horizontal displacement. So we're going to take that horizontal displacement, and from the center, we're going to scoot 5 over. 1, 2, 3, 4, 5. Put a point there. 1, 2, 3, 4, 5. Put a point there. Those are the vertices of our hyperbola branches, and we're going to go ahead and label those. So if my center is 2, 4, and I go 5 to the right, I'm now going to be at 7, 4. And if my center was 2, 4, and I go 5 to the left, I'm going to be at negative 3, 4. My x values are changing, not my y values. So once I have those vertices, I can simply draw in the branches by going out close to the asymptotes and staying close to the asymptotes. Allow the asymptotes to give the hyperbola branches their shape. Sometimes I have students who just kind of like, whee, throw the branches in there, and even though they're anchored in the correct spot, they're not getting the right shape because they're not following the asymptotes. Now, I told you there was another way to sketch this, and in all fairness, it's probably the more popular way to sketch the hyperbola. That version, that more popular version, only needs the center, the horizontal displacement, the vertical displacement, and the direction. They skip the slope of the slant asymptote, and it gives an accurate hyperbola, but I'll tell you the problem I have with it in just a second. Here's how they work that out. The teachers and publishers that use that version start with the center, over 2, up 4, put a point there, label it, and then from the center, they take the horizontal displacement, in this case it's 5, and they go over 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then they take the vertical displacement and they go up 3. 1, 2, 3, and they go down 3. 1, 2, 3, and they put points there. This version is oftentimes called the box version because once they have those 4 points laid out, they simply draw a box connecting those 4 points where those points are the midpoints of each side of the box. From there, they just go corner to corner to draw in the asymptotes. And then from there, once you know it opens in the x direction, they just put the vertex of the hyperbola branches right there on the edge of that box. Honestly, that version seems a little bit simpler. The problem that I have with that version is that it completely ignores the fact that there are slant asymptotes and that those slant asymptotes have slopes. I've seen standardized test questions that are asked about the slopes of the slant asymptotes, and students who only know the box method tend to get stuck on that question. They tend to not know what to do because they've never dealt with the slopes of those slant asymptotes. It wouldn't be horribly hard. It wouldn't be too terribly difficult to get the slopes from the box method, but I always want to see the slopes of the slant asymptote written out in the problem. Let's try another problem. All right, so looking at this equation, all I really see is kind of a big old mess. It's hard to tell the shape when you have a mixed up, messed up version of all the original equations. So undo the crazy messiness. I'm going to go ahead and distribute my 4. I get 4x squared plus 32y plus 24x equals 16y squared minus 84. And then I need to get my squared terms on the same side. So I'm going to subtract 16y squared. And so I have 4x squared minus 16y squared plus 32y plus 24x equals negative 84. I'm not too worried about the x term, the y term, and the plain old number term. All the information about the type of shape we're dealing with is found in the squared terms. And what I see is an x squared and a y squared, but one is positive and one is negative. Students sometimes make a mistake of thinking they can tell from right here, the positive x squared term, that it's going to open in the horizontal direction. But you can't actually tell until the end when it's in professional form because the math changes throughout the problem. Let's go ahead and attack this problem. Let's get our x's with our x's and our y's with our y's. So I have 4x squared plus 24x minus 16y squared plus 32y equals negative 84. And now I group them. Keep the negative with the 16 and bring in your own plus sign. Factor out the 4. Factor out the negative 16. Double check that you factored properly. And now we complete the square. 1/2 of 6 is 3. Square it. Add that to both sides. And when I do, I add the 4 times 3 squared. Now I go 1/2 of 2, which is 1, square it, add that to both sides. And then I form my perfect squares. First term, last term, middle sign squared, minus 16 times first term, last term, middle sign squared equals, adding all of that together, I get negative 64. Now remember, with both circles and ellipses, if we had the squared stuff equaling a negative number, they were degenerate circles or degenerate ellipses, which in this case had no graph because you can't have a squared term plus another squared term equaling a negative number. But with a hyperbola, because of the negative coefficient, it is possible to have a positive number minus another number equal a negative number. And so this is not a degenerate hyperbola. Degenerate hyperbolas exist, but they don't happen when the squared stuff equals a negative number. If you get a negative number with a hyperbola, you keep going. Like this. I'm going to divide by negative 64, divide by negative 64, divide by negative 64. And now looking only at the signs, what I have on the x term is a positive divided by a negative. So a positive divided by a negative means this negative can pull out to the front. On the y term, I have a negative divided by a negative. A negative divided by a negative is positive, and so those negatives cancel, and the y term is going to become positive. Now looking at the coefficients, I'm going to divide the top by 4, divide the bottom by 4, divide the top by 16, divide the bottom by 16. So I have x plus 3 squared over 16, and the whole term is negative because that negative has pulled out of the x term. And then I have a positive y minus 1 squared over 4 equals 1. Drop parentheses all the way down. The signs just live outside their x or y terms. And so here is my professional form. Looking at the professional form, what is the center? We know it's going to be opposite, opposite. So it's going to be negative 3, positive 1. My horizontal displacement is on the bottom of the x term, it's the 4. My vertical displacement is on the bottom of the y term, it's 2. The slope of the slant asymptote is plus or minus rise over run. So it's the vertical displacement over the horizontal displacement. It's plus or minus 2/4, which we can reduce. It's going to be plus or minus 1/2. And then finally, the hyperbola opens in either the x direction or the y direction. So we look back at our professional form, and whichever term is positive, that is the direction that the hyperbola is going to open. So this hyperbola opens in the y direction. Let's go ahead and sketch it and see what we have. So from the origin, I go -3, 1, 2, -3, +1, put a point there. I'm going to label it as -3, +1. Then from this center point, I'm going to grab the slopes of the slant asymptotes. I'm going to go up 1, over 2, put a point there, or I could go down 1 and back 2, put a point there, draw in that asymptote. Then I'm going to go up 1, back 2, put a point there, down 1, over 2, put a point there, draw in that asymptote. There we go. And now I know it opens in the y direction. So between horizontal and vertical displacements, which one represents the y direction? The vertical displacement represents the y direction. So this thing is going to open up and down. It's going to open in the y direction. So from the center, I'm going to move 2. I'm going to move the vertical displacement. I'm going to go up 2, put a point there. I'm going to go down 2, put a point there. And I'm going to label both of those points. I was at -3, 1, but I went up 2, so I'm now at -3, 3. And I went down 2, so I'm at -3, -1. So from this point, I'm going to go out to the asymptote and just stay close to the asymptote and allow the asymptote to give the hyperbola its shape. And that's it. That's what this hyperbola looks like. Hyperbolas are part of that family of shapes known as conic sections. If we look again at a double-napped cone, and we chop this vertically through both sides, through both cones, and then we separated those pieces and looked at them on the plane, you would see this up and over the edge parabola-looking shape happening, and a down and over the edge parabola-looking shape happening. That's where the hyperbola is coming from. It's a vertical chop completely through both cones of a double-napped cone. Now let's look at it again. If we had our double-napped cone and we chopped this directly through the center and separated those pieces, opening them up on a plane so we could look at them, what we would have is 2 diagonal lines intersecting right at the dead center. You'd see the back side of the cone and the front side of the cone. This is what happens when a hyperbola degenerates. A hyperbola degenerates when the squared terms add together to equal 0. And a hyperbola degenerates into 2 intersecting lines that would have been the asymptotes, except now they're solid because the hyperbola itself has degenerated. Let's go back to the equation we just worked on. Let's say we got to this part of the equation, only instead of equaling -64, it equaled 0. Let's go from there. So we have done some math and found ourselves here. We recognize this as a degenerate hyperbola because the squared terms equal 0. That's the only time a hyperbola degenerates. Again, if it equaled a negative number, we divide by that negative and we keep on going. But in this case, it's degenerate, and we can't just divide by 0, divide by 0, divide by 0. That makes no sense. So how do we deal with a degenerate hyperbola? Well, backing up here, we basically pretend that it's not degenerate, and we're going to keep on going. Here's how. We need to remember that each of these terms is over 1, and we're going to deal with those coefficients the same way that we normally would. We're going to divide the top by 4, divide the bottom by 4, divide the top by 16, divide the bottom by 16. And in doing that, we get x plus 3 squared over 1/4 minus y minus 1 squared over 1/16 equals 0. Ignoring the fact that it equals 0, we're going to keep on going. Drop parentheses all the way down. We get x plus 3 over 1/2 squared minus y minus 1 over 1/4 squared equals 0. So our center would be -3, +1. Our horizontal displacement would be 1/2, and our vertical displacement would be 1/4. Now at this point, we ask, what would the slope of the slant asymptotes be? The slopes would be plus or minus rise over run, the vertical displacement over the horizontal displacement. And this is where we get a little bit of math to do. We have 1/4 divided by 1/2. That's going to be 1/4 times 2 over 1, so that's 2/4, which equals 1/2. The slopes of the slant asymptotes are plus or minus 1/2. So we have our slopes and we have our center, and it's time to sketch. So I'm going to go to -3, 1, 1, 2, 3, 1, put a point there, label it, -3, 1, and I'm going to sketch in both asymptotes. Only instead of being asymptotes, instead of being dashed like asymptotes are, these lines are just going to be solid. It's a degenerate hyperbola, and a hyperbola degenerates into two solid intersecting lines. So we're going to go up 1, over 2, put a point there, down 1, back 2, put a point there, and this time it's just going to be a solid line going through there. Again, up 1, back 2, put a point there, down 1, over 2, put a point there, and it is a solid line intersecting those points. That is the degenerate hyperbola. It's two solid lines intersecting to make an X. Now, this is the mathematically correct way to approach a degenerate hyperbola. You ignore the 0, have the whole thing be over 1, divide the coefficients, etc. But there is a shortcut to be found. Compare the coefficients that we have in the step where we determined this is a degenerate hyperbola. In the step where we found the squared stuff equaled 0, look at these coefficients and compare them to the coefficients that we ended up with, 1 and 2. It'll be easier if I back up just a step. Before I reduce this fraction, I had 2/4. Comparing 2/4 to 4 and 16, what you find is that the slopes of the intersecting lines, again, they're no longer asymptotes, they're lines. The slopes of the intersecting lines are equal to the square root of the coefficient on the x term over the square root of the coefficient of the y term. So you would get 2/4, which is 1/2. And of course you have the plus or minus because there's two of them. So let's start this problem again with the shortcut in mind this time. We have the squared terms equaling 0. We know it's a degenerate hyperbola, and a hyperbola degenerates into two solid intersecting lines. Now we need the center, and we can find that center here already. It's opposite, opposite. It's going to be -3, 1. Now all we need is the slope of the slant asymptotes, only instead of making them asymptotes, we'll make them solid intersecting lines. As you know, slope is always rise over run, and rise would be a y term over an x term. But because it's degenerate, imagine that a good hyperbola has gone bad, and that means it's misbehaving in all sorts of ways. So we're going to flip this over, and it's going to be the square root of the coefficient on the x term over the square root of the coefficient on the y term. We look back, we see the square root of the coefficient on the x term, so it's the square root of 4, over the square root of the coefficient on the y term, so rad 16, that gives us 2 over 4, that gives us 1/2, and again it's going to be plus or minus because there are two of them. Doing this shortcut allows us to get this exact same picture, but in a much quicker way. Let's try again. Let's say we were doing some math, and we got to this point here. We can see pretty quickly that it's going to be a degenerate hyperbola because we have squared terms equaling 0. And that is the only time that a hyperbola degenerates. I'll say this again because students do tend to forget this a lot. If it equaled a negative number, negative numbers are okay with hyperbolas. We would just divide by that negative, and we would keep on going. But that's not the case when it equals 0. From here, we're able to use our pretty quick and easy shortcut. You could use the long way if you wanted to and say that both terms are over 1 and then divide the coefficients away, but the shortcut works and the shortcut's pretty quick and easy, and so that's what I choose to do. I know that my center is going to be opposite, opposite. So my center is going to be 2, -3. And then the slope of the slant asymptotes, again, I'm not going to sketch asymptotes. I'm going to sketch solid lines. But the slope of the slant asymptotes can be seen as the square root of the coefficient on the x term. You can ignore the signs completely, over the square root of the coefficient on the y term. Now remember, normally we would say rise over run, that's y over x, but with a degenerate, it's misbehaving, so it's going to flip over. So what we get is plus or minus 3 over 5. I brought in the plus or minus myself because there are 2 intersecting lines, and then we could sketch from there. Sketching this is as simple as going over 2, down 3, put a point there. And then we're going to go up 3, 1, 2, 3, over 5, 1, 2, 3, 4, 5, put a point there, down 3, 1, 2, 3, 1, 2, 3, 4, 5, over 5, draw a solid line through, and then go the other way, up 3, 1, 2, 3, back 5, 1, 2, 3, 4, 5, and then down 3, 1, 2, 3, over 5, 1, 2, 3, 4, 5, and draw a solid line on through. Big dots fix everything. And there we go. That is our degenerate hyperbola. It's degenerated into 2 solid lines, and these are the slopes of those lines. All right, I hope that makes sense. Let me know if you have any questions. Have a great day.